Hello students, let us learn about heat, that is what is heat and how it appears in matter and how it affects the matter in all its three states. We know this matter exists in three states, they are solids, liquids and gases. In the solid state, a body has a definite volume and it is almost incompressible. It also has a definite shape independent of space available to it. In the liquid state, also matter possesses a definite volume and little incompressibility, but liquid has no definite shape and automatically it takes the shape of any vessel into which it is placed. In the gaseous state, matter has neither fixed volume nor the fixed shape. A quantity of gas introduced into any closed space immediately spreads out to fill the whole space available to it. Also, gas shows considerable compressibility. When we supply this heat to the matter, the first immediate effect we observe is rise in temperature. Next, it expands the matter. Let us consider the expansion of solids. This property of the solids we will study by the quantities known as coefficients. They are coefficient of linear expansion, that is alpha, coefficient of areal or superficial expansion, that is beta, and coefficient of volume or cubical expansion, that is gamma. When the heat is supplied to the solid in the form of rods or wires, then there will be expansion along the length. It is known as linear expansion. This quality will study by the coefficient known as alpha, coefficient of linear expansion. It is defined as ratio of increase in length for 1 degree rise in temperature to its original length. When the solid is in the form of plates, the major dimension it possesses is area. So, by supplying heat there is expansion in area. It is studied by the quantity known as coefficient of areal or superficial expansion beta. It is defined as the ratio of increase in area for 1 degree rise in temperature to its original area. But when the solid is in the form of cubes, that is spheres or cylinders, there will be expansion in volume. This is studied by the quantity known as gamma, that is coefficient of volume or cubical expansion. Ratio of increase in volume for 1 degree rise in temperature to its original volume. By laying telegraph and electric poles, there must be sufficient sag for the wire. During winter, when contraction takes place, these poles they are pulled on either sides because of the contraction of the wire and they get uprooted. To avoid this sag must be given. Similarly, while laying the railway tracks, there must be sufficient expansion channel between two rails to allow for expansion during summer. Similarly, here these are the expansion channels. Here platinum wire is fused into this glass tube. These two are having same coefficient of linear expansion. When the bulb is switched on, because of current supplied to it, the platinum gets expand. If it is not with the platinum, because of uneven expansion of the material and the glass may break. In this electric bulb, platinum wire is fused into the glass bulb. These two materials are having same coefficient of linear expansion. When electricity is given to the bulb, because of which heat is given and there is similar expansion for both the materials and bulb will not break. Otherwise, because of uneven expansion, the glass may break. Because of the same reason, concrete roads are not laid in single pace, but in section to allow for expansion during summer. When metal tapes are taken to measure the length, it must be with invar steel because it is having very least quotient of linear expansion. Otherwise, it will give different measurements depending upon the seasons. When a metal sheet with a hole is heated, the diameter of the hole increases because of heating. The pendulums of the wall clocks also must be with the invar steel because of least linear quotient. A pendulum of a wall clock expands in summer and contracts in winter. As a result, it loses time or goes slow in summer and gains time or goes fast in winter. For showing correct time, the pendulums of wall clocks are made of invar steel, which is the mixture of nickel and steel. Such pendulums whose length remains constant are called compensated pendulums. Another application of expansion of solid is bimetallic strip. Here this strip is made of two different materials having different linear coefficient. On heating, these are expanding in different manner and bending. This bending may be used in electric circuits to close or break the circuit, because of which the temperature is remaining constant. These bimetallic strips are utilized in making thermostats. A thermostat is a commonly used in electrical appliances, namely in automatic electric irons, refrigerators, etc. Bimetallic strips are also used in fire alarms, relay for opening and closing electric circuits. As we know, liquid requires a container, it will have only volume expansion, but here the container also will expand. So, by considering the container expansion and by neglecting the container expansion, it is having two types of volume expansions. They are apparent expansion and absolute expansion. When heat is supplied to this container with a liquid up to the level P, immediately container alone expands. This happens within no time and capacity of the container increases, the level of the liquid falls to Q. Next, immediately the liquid takes the heat and liquid also expands. The expansion of the liquid is more compared to the expansion of the solid and the level rises to R. Here what we are observing is the rise of the level only from P to R. What is really happening is the expansion of liquid from Q to R. So, when the expansion is considered from P to R, container expansion is neglected and it is the apparent expansion of the liquid. When expansion of the liquid is considered from Q to R, that is real or absolute expansion of the liquid. When the gas is heated under the conditions which prevent its expansion, for instance, in a closed vessel, its tendency to expand will cause the gas to exert an increase in pressure. In the case when gas is allowed to expand and is prevented to receive any heat, the temperature of the gas will fall, that is, it cools. Any change in pressure of the gas will affect the volume of the gas. Thus, in the case of gases, we have three variables: volume, pressure and temperature. These variables are mutually depends upon one another. When heat is supplied to the gas, all these three physical quantities varies at a time. To get the relation among these quantities, the laws are developed by Robert Boyles and Charles. In these, we get the relation between two quantities by keeping the third one constant. This Boyle's law states that the volume of a fixed mass of gas at constant temperature is inversely proportional to its pressure. V is inversely proportional to P, that is PV equal to constant. If V1 and V2 are the volumes of a gas at P1 and P2 pressures for a given mass of gas M, by keeping temperature constant, then P1 V1 equal to P2 V2, which is equal to constant. This law holds good for any gas at high temperatures and low pressures. It is disobeyed by gases at low temperatures and high pressures. The gas that obeys Boyle's law at any pressure and temperature is known as ideal gas. First Charles law or Charles law at constant pressure. The volume of a given mass of gas at constant pressure increases by 1 by 273 times of its volume at 0 degree centigrade for every degree centigrade rise in temperature. So, volume of gas at any temperature T is given by Vt equal to V0 into 1 plus T by 273. Second Charles law or Charles law at constant volume. The pressure for a given mass of gas at constant volume increases by 1 by 273 times of its pressure at 0 degree centigrade for every 1 degree centigrade rise in temperature. So, pressure at any temperature is given by Pt equal to P0 into 1 plus T by 273. From two Charles laws, we have the equations for Vt and Pt. When we substitute minus 273 degree centigrade into these equations, we get volume equal to 0 and pressure equal to 0. However, this does not happen really, as the gas would liquefy or even solidify before reaching this low temperature. But because the volume and pressure of the gas become 0 theoretically, minus 273 degree centigrade is called the absolute zero of temperature. This absolute temperature is the lowest possible temperature that is conceivable. Absolute zero temperature may then be defined as the lowest possible temperature at which the pressure and volume of the given mass of gas becomes 0. Here this is Kelvin scale and this is centigrade scale. This minus 273 degree centigrade is taken as 0 degree Kelvin. This is positive side of the scale and this is negative side of the scale. The 0 degree centigrade, which is the melting point of the ice, converts as plus 273 degree Kelvin, and boiling point of water 100 degree centigrade converts as plus 373 degree Kelvin. Here the length of the degree on both the scales are same. If T be the temperature on the absolute scale corresponding to T degree centigrade, the relation between capital T and small t is given by this. On this absolute scale, the Charles laws changes their form as V1 by T1 equal to V2 by T2 at constant pressure, and second law P1 by T1 equal to P2 by T2 at constant volume V for a given mass of gas M. Now, let us derive the gas equation which indicates the relation among volume, pressure and absolute temperature capital T. Consider V1 be the volume of given mass of gas at pressure P1 and absolute temperature T1. Now, by keeping temperature constant, pressure is changed to P2, accordingly volume is changed to V. Here, as we are keeping temperature constant, we can apply Boyle's law. So, we get the equation V equal to P1 V1 by P2 is first equation. Now, by keeping pressure constant, volume temperature is changed to T2, accordingly volume is changed to V2. Because we are keeping pressure constant, we can apply first Charles law and we get the equation V equal to V2 T1 by T2, that is second equation. From these two equations, we have P1 V1 by P2 equal to V2 T1 by T2. By getting all initial values to one side, the final values to the other side, we have P1 V1 by T1 equal to P2 V2 by T2, which is pressure into volume by absolute temperature is constant. When the mass of the gas is considered as 1 gram mole at normal temperature and pressure, this constant value is capital R, and which is known as universal gas constant, and its value is given by 8.31 joule per mole per Kelvin. Now, let us consider the compressions and expansions of gas. We know heat appears in matter as kinetic energy. So, whenever heat is supplied to the matter, its internal energy increases. But when we consider the isothermal process, we will take the gas in conducting vessels provided with a piston. So, whatever the increase in internal energy takes place, that is conducted away to the surroundings and temperature remains constant. That means internal energy of the system remains constant. In this isothermal process, temperature of the gas is constant, but the pressure and volume change. When the work is done on the gas by moving the piston in downward direction, volume decreases, pressure increases, accordingly temperature increases. And when piston is moved in outward direction, the gas expands at the cost of its internal energy, its volume increases, pressure decreases and temperature decreases. Here these changes in temperature comes to original condition because piston and walls of the container, they are of conducting in nature. Here in this process, as the temperature is remaining constant, the internal energy of the system remains constant. So, Boyle's law holds good here. When we consider the adiabatic process, because we are taking the gas in non-conducting vessel and provided with the piston, here whatever the changes are taking place, they remain as it is. In this adiabatic process, pressure, volume and temperature of the gas changes. Here when the piston is moved inward direction, pressure increases, volume decreases and temperature increases. And when piston is moved in outward direction, volume increases, pressure decreases and temperature decreases. Here whatever the changes are taking place, they remain as it is because the walls of the container and the piston, they are of non-conducting in nature. So, here Boyle's law does not hold good. The equations which hold good are PV power gamma equal to constant, TV power gamma minus 1 equal to constant, P power gamma minus 1 by T power gamma is constant, where gamma is the ratio of specific heats at constant pressure and at constant volume. This is applied in compression of air in diesel engine or in an air compressor. Expansion of steam in the cylinder of a steam engine, expansion of hot gases in an internal combustion chamber and propagation of sound waves through air. Students, so far we have studied about the effect of heat on matter and also we have derived the gas equation and we have observed the processes adiabatic and isothermal. Now, let us observe the transmission of heat, that is how this heat is transmitted from one point to the other point, and we know this can be done in three ways: conduction, convection and radiation. See, in this conduction, that is one end of the metallic rod is heated, heat is transferred from one end to the other end in the direction of fall of temperature without the actual motion of the particles of the medium. Students, just now we observed that heat is transmitted in solids by the process of conduction. When we consider the liquids, here heat is transmitted by the process of convection because of the density difference. When liquid in a container is heated, first lower layer gets heated up and its density decreases and it comes up. Next layer gets heated up, then also its density decreases and it comes up. In this way, the complete liquid gets heated up because of the density difference. This convection is also possible in gases, and in so many examples we will observe that this convection is taking place. When conduction and convection are considered, material is essential there, but without the material medium, heat can be transferred by the process of radiation. As we know, we receive the heat from the sun, and only around the earth through 400 kilometers there is atmosphere, that is matter, and we are receiving above that the heat of the sun. So, here heat of the sun is travelling through the vacuum, that is known as radiation. The substances which allow the heat to pass through them by the process of conduction are known as conductors. If they do not pass the heat, they are known as insulators. Let us see the applications of these conductors and insulators. All the metals such as silver, copper, aluminum, mercury are good conductors. Cooking utensils are made of metals or their alloys because they absorb heat easily and efficiently. In winter, we feel cold or on touching an iron rod because the iron rod absorbs heat from our hand. Wool is used as winter clothing because it does not allow the heat of the body to escape. It also protects the body from outside cold air. Chimneys and ventilators works on the principle of convection. Warming of the rooms are also resulting from principle of convection. Land and sea breezes are resulting from convection currents. Trade winds also are the examples for convectional currents. Students, after this transmission of heat, let us study the other branch of heat, that is thermodynamics. This thermodynamics deals with the relation between heat energy and the mechanical energy, or in the broad sense, heat energy and other forms of energy like electrical energy, chemical energy and light energy. This thermodynamics comprises two laws. They are: the first law of thermodynamics states that the heat energy supplied to a system is equal to the sum of the increase in internal energy of the system and the external work done by it. Let dQ be the amount of heat added to the gas. A part of this is utilized in increase the internal energy by raising the temperature. The other part is utilized in expanding the gas by a volume dV against a constant pressure P. Let du be the increase in internal energy. Work done in expanding the gas is equal to P dV. Then the first law gives us heat energy supplied equal to increase in internal energy of the system plus external work done by the gas in expanding, that is dQ equal to du plus P dV. Second law of thermodynamics states that it is impossible for a self-acting machine unaided by an external agency to transmit heat from a point at lower temperature to a point at higher temperature. Second law of thermodynamics is stated in different ways. The following are the two most widely accepted statements. Clausius statement: it is impossible for the heat to flow from a body at a lower temperature to a body at high temperature without the aid of external agency, or heat cannot by itself flow from a cold body to a hot body. Kelvin statement: it is impossible to derive a continuous supply of energy by cooling a body below the coldest of its surroundings. We see the applications of this second law in compressors in refrigerators, cold storage units and air conditioners, and engines used in diesel, petrol and systems. As a consequence of this law, a property called entropy is invented. Students, in this chapter of heat, we have studied about the expansion of solids and liquids, compression and expansion of gases, and we devised the new scale called absolute scale, and we have derived the gas equation, the three modes of transmission of heat, and finally we have studied about the two laws of thermodynamics. Students, I hope you understood the lesson well. Till we meet again, goodbye.
Further clarification, contact the Additional Secretary, State Board of Technical Education and Training, 7th floor, BRKR Bhavan, Tank Bund Road, Hyderabad 500063. Fax 040-322-0546.